Okay, thank you very much, Paul, for the presentation. Just at the last check, can you hear me? Can you see the presentation?
Yes, everything looking good.
Okay, perfect. So, well, again, thank you very much. I'm very happy to be here sharing with you my recent work and be part of this colloquium. In this presentation, I will talk about the potential of the deep learning in solar physics, and I will show you some interesting applications to some of our problems. To start from the beginning, let's define some concepts. If we consider machine learning as the set of statistical techniques which give the computers the ability to progressively improve the performance on a specific task with data with a very general program, so without being explicitly programmed. Among those techniques, deep learning can be seen as a subset of neural networks, which is larger and more complex, and which shows a very good performance in terms of speed and accuracy. And exactly because of that, this field is continuously evolving and growing. The general overview of this field is that the neural networks are very flexible and versatile. This means that we can solve with neural networks the same problems where we were using standard machine learning techniques. For example, classification problems with k-means, dimensionality reduction with principal component analysis, regression problems with Gaussian processes. So with deep, in the sense of large and complex, neural networks, we can deal better with more data. So we can achieve also better results in general than standard techniques. And in this slide, here I show you a rough estimation of the size of spectropolarimetric data observations and how this size is increasing with time. We know that also our models nowadays, because we have more physical ingredients, they take also more time to analyze the data. So at least in my opinion, one of the motivations is that given the speed and the performance of these deep learning techniques, they can help us to deal with the amount of data that we are already producing or we will produce with new telescopes. So before showing some of our results, I just wanted to highlight some examples in the literature where these techniques are being used. For example, in flare prediction, analyzing the features of each active region and trying to predict what would be the probability and the magnitude of a flare. The detection of far-side solar active region. That is also very important in space weather forecasting. Another example can be fast and robust differential emission inversion code to overcome problems with bad convergence in some areas, or effective segmentation programs like the one I showed you here, where they can study the evolution of the coronal holes. I also just want to highlight two more where also using neural networks, we can get a very good estimation of the transversal velocities in the solar surface, much better than the common local correlation tracking, which allows us to analyze small vortices And one of my favorites, in my opinion, the solar image classification that is very useful. For example, nowadays that we have a large data set of observations and one needs to find a specific target for an analysis. So this will be very useful. So to understand the next examples, let's start summarizing a simple case. An artificial neural network is composed by several free parameters and that modify the input to get an output. This transformation at each location is described by this formula. Here we see that the input are scaled by the factor usually called weight and a constant. And to this result, we apply a nonlinear function. This is probably one of the most important parts of a neural network because it's which gives the nonlinearity to the neural network. So we are able to map very complex relations between input and output. Once we have the architecture, we have to define our goal and then our merit function. So what we want to do. For those cases, we also have examples because we need to show or to teach this neural network the examples that we want to learn, the relation that we want to learn. And finally, we will optimize this neural network with thousands or millions of parameters to learn this relation. A big step in pattern recognition using images is a special type of neural network that is called convolutional neural network. This neural network takes the image as a whole, not as a set of pixels. So the basic elements in this case is a convolution that affect the whole image at the same time. Those convolutions will highlight some spatial patterns, like the one I showed you here, that will be important for learning how is the mapping between the input and output. So in particular, these neural networks has been designed for looking how each pixel is related to the surrounding. And the first example that comes to my mind when we are talking about the light of a pixel and the relation with the surroundings is the blurring effect of a point spread function. An image corrected from the effect of the PSF can help us to detect and characterize small features in the surface of the sun, or improve the estimation of the magnetic field of the magnetic flux in magnetograms. So the helioseismic magnetic imager HMI on board of the Solar Dynamics Observatory provide this information with a cadence better than 1 image per minute. So, but the trade-off between a full disk observation and the spatial resolution makes HMI not enough sometimes for analyzing the smallest scales. So our motivation was exactly that, to develop a neural network to do fast deconvolution and super resolution with HMI. And here you can see an example of that, the original in the upper part and the result of the neural network in the lower part, and the same in the magnetogram. So how we did that? To do that, we synthesize continuum and magnetogram images from MHD simulation, and we applied the PSF, the HMI PSF. So we had to train a neural network to learn the relation between the synthetic images with the PSF and without the PSF. After finishing the training, the neural network is able to do the deconvolution in a very fast and robust way. And as you can see, for example, this is a particular example where we take a magnetogram in HMI. Here in the middle panel, we see the output of the network, and we were comparing this example with the same field of view in Hinode to compare how sensitive is the magnetic field to the resolution and how spread is the magnetic flux in this first image, and how important is to have these tools. One of the key points is that we usually use, for example, the Richardson-Lucy algorithm to do the deconvolution. However, it introduces artifacts due to the noise, and it will create high spatial frequency signals like the one you see in the upper part of the image. So in principle, we need to dump these very high frequency signals, introducing our knowledge about this and so our prior about what we expect to have after the deconvolution. However, in this case, the output of the neural network is not affected by this problem, not only because also we were use noise during the training, but also because here the neural network is learning this prior during the training process. So we are showing to the network what is how the typical sun should look like, and it should then produce this very high frequency signals. So the motivation of having high spatial resolutions is not, of course, not only from space, but also is important when we observe from the ground. And here, what I show you is that, of course, from the ground, we use adaptive optics to correct the atmosphere aberrations, but it is not enough, and we usually need to, a posteriori, use a technique to correct the smallest aberrations to really do high spatial resolution observations. We do that at the Swedish Solar Telescope with a technique called multi-object, multi-frame blind deconvolution, and we can achieve our results with a precision like the one you see in the image. The only drawback of this great technique is that it takes around weeks or months to do the processing of one of these images if we don't have a big cluster, for example, to do the calculation. So 2 years ago, by Andrés Asensio Ramos and collaborators, it was shown that a neural network could be trained to mimic what this program was doing. So here in the second column, you see the output of the neural network, what the program was doing, and the raw image. This is, of course, this is much more complex than the original problem from the telescope, from the satellite. But they were showing that this reconstruction can be done in almost real time. So since then, we are improving this system. So probably in the future, we can have it in the Swedish Solar Telescope, and we can have a real-time image reconstruction. And one of the points is not only to have to improve the resolution of the images, but also to improve the decisions of the observers while they are doing the observation in the telescope. Once we have the data, we would like to infer physical quantities like the magnetic field. However, these polarization signals, where we can extract the information of the magnetic field, are usually very weak and close to the detection limit of our instrumentation. There are several ways to increase the signal-to-noise ratio. One of them could be a time average or spatial average. However, we could remove or lose some spatial or temporal information that could be important for our analysis. Also, we can use the spectra. We can use the spectral information, the spectral shape of the polarization signals, using principal component analysis, for example, to filter the noise. However, in some cases, like in Fabry-Perot spectrograph data, we don't have a good sampling. We have a few points in the spectral line. So it would be very difficult to exploit all the information that is present in the spectral line. So the question that I want to just say in this case is, okay, so cannot we use then the spatial information to improve these results? And this is something that some people have been trying in the inference. So when we extract information, for example, in the magnetic field, by doing an inversion where the pixels are coupled. So you expect some smooth behavior in your field of view, or sparse inversions where you expect that when you project the physical quantity into a spatial domain, it will be sparse. So these are many ways to introduce this information of this spatial correlation. But here, what I'm proposing is just a little bit different. So cannot we use a neural network then to improve the estimation of the signals? I have been showing these convolutional neural networks that also look to the pixels in the surroundings. So cannot we improve the estimation of the signals and reduce the noise by looking at those surroundings pixels? So okay, let's do that. In principle, is easy, right? We just need noisy images. We need clean images, so we can train a neural network to do this step between the input and the output. But my question in this case would be, do we have data with and without realistic noise? Because, for example, the characterization of the noise is not trivial. And when the data has been processed multiple times. I have been showing how we can do this in reconstruction and the convolution. So at the end, the data that we have introduced some correlations between the pixels. So the noise is not more independent from pixel to pixel, or it does not have a simple distribution. So how can we deal with that? So in 2 years ago, Lettinen and collaborators, they suggested another method where the training is done instead of using a noisy and clean image, 2 different images where the signal is the same, but the difference is the noise realization. So we are training a neural network to be able to go from a noisy input to a noisy output. As this noise is not correlated between images and is random, the neural network will not be able to fit the noise, but it will be able to extract the information, the spatial information from the input and produce a clean output. One of the main points of this method is that this method does not require prior information about the noise or a clean image. So it's exactly perfect for our motivation. We just need many noisy observations and we can train a neural network to do that. In the real life, it's a little bit more difficult. So at the end, what we have is 2 monochromatic images very close in time, where the main difference is the noise realization. So under this assumption, we can train one of these neural networks. To really test these methods, we created a synthetic dataset. So we synthesize spectral profiles from MHD simulation and in some spectral lines. And what you see in those panels is the first row is the training of the noisy clean method. And the second row is the training of the noisy method. So in the lower part, we have noisy pairs of images. What you see specifically in those rows is the noisy input, the original from the simulation. This is the output of the neural network after cleaning this noisy input, and the difference to check how good was and to validate how good was the neural network. And as you see from the numbers on top of these panels, they achieve a very similar result. So this is showing us how we can use this method to train a neural network with our observed data, with our noisy data, and get and reduce the noise using this spatial constraint. After cleaning each wavelength in an independent way, we can reconstruct the whole spectral profile. Here you see some Stokes Q and Stokes P examples. And in the estimation of the signals, we also implemented an uncertainty calculation. And in those pixels, you see how the output of the neural network is compatible with the synthetic profiles within this red band. That is the uncertainty that we have estimated. So we did the next step, that was to take our data and to do the same with our data. So we took many monochromatic images with a very good cadence, so where the main difference was the noise. And this is one of the results of the neural network after applying the observed image, and this is the output of the neural network. So what we see here, and this is one of the main points, is that this is a monochromatic image close to the core of in a Stokes cube of the calcium-2 line at the 8542 angstrom. We see that the polarization signals coming from the chromosphere are very weak, and this method that use the spatial correlation to reduce the noise can help a lot to recover these weak signals and then infer much better the magnetic field. And this is another example in a Stokes V for the same spectral line. So we did exactly the same, right? Because at the end we are working with Stokes profiles. So we clean each wavelength in an independent way, and then we have the whole profiles. Again, some Stokes Q and V profiles, and one can see the improvement in the reconstruction. In my opinion, one of the most surprising aspects was that the profiles were smooth. However, the neural network does not have any information about what wavelength I'm cleaning. So this is showing us how the information of those profiles were in the data just hidden by the noise. The neural network was able to recover them by looking to the closest pixels. And one different way to check how good was the reconstruction, because when we are dealing with observed data, we don't have the answer, right? Was to compare with the average profile of the whole time series. We checked that that those profiles were very similar. So we can obtain a profile very similar to the average, but without losing the temporal evolution of these signals. And in my opinion, one of the interesting things was that the neural network is really learning the distribution of the noise and to characterize the noise in a sense, because what I'm showing here is the lower part of the image is the output of a neural network that was trained with real data, so with real noise. And the upper part of the same image is a neural network, another neural network that was trained with a synthetic noise, so with a typical Gaussian noise that is independent in between pixels. So here you can see that the performance of the neural network is much worse because it was not catching the information of the spatial scale of the noise and the correlation between those pixels. So after that, one can ask, yeah, okay, that you have a spectrum, right? Why not to include the information of the spectrum? In this case, one can do the same. One, instead of training two monochromatic images, we can train one profile at one time frame and another spectral profile very close in time. So as you see in the comparison between the only spatial and spectral, one can see an improvement in the reconstruction of the signals. In the spectra, it's not very evident, but one of the important points when we include the spectral information is that the neural network is no more general, it's now specific, because we have trained a neural network to deal with a spectral line, with a certain sampling. So we cannot use the same neural network with another instrument, with another spectral sampling. So it will not work while the first one can do it. Also, another problem is we usually want to have a high variety of profiles when we do this training, right? But usually profiles with very high velocities, so very high velocity and redshifts, they evolve fast. In the sun, things that have high velocities usually evolve fast. So it's difficult to find profiles with large velocities that are almost constant with time. So this was also one of the problems to create this data set to be able to train the neural network. So once we have the data and we want to extract the information, we would like to extract the information of the physical quantities of the atmosphere behind these signals. And for that, we use what we call inversion codes, where they find the physical quantities that are able to generate the same signatures that we observe. So when we do inversions, we want to have many spectral lines, because then we will constrain much better the whole atmosphere and all these quantities. Usually in the field of view, we have thousands, millions of pixels, and these spectral lines are usually also formed under complicated conditions, like non-local thermodynamic equilibrium or partial frequency redistribution. So at the end, it will be very difficult, or at least it will be very time-consuming to solve this task. And of course, this is not a new idea. And people, since 20 years ago, they have been trying to accelerate these spectropolarimetric inversions using neural networks. And they have shown how we can infer and estimate the temperature, the velocity, and also here the magnetic field as good as when we use standard techniques, but in a much faster way with values around 1 million times faster. Here I show you also some examples that are more recent by Ivan Milic and Alberto Sainz-Dalda. They have been also in this colloquium some time ago, so you also probably remember one of these plots. And they have been analyzing the performance and the limitations of this technique in different scenarios using a pixel by pixel approach. So here at the end, what we are doing here is to map the Stokes profiles with the physical quantities. So the neural network is learning how to map this nonlinear relation between Stokes profiles and physical quantities. One can also use a neural network as a quick shortcut in case we only want to have a good guess model. For example, one can train a neural network for an inversion of a lower resolution and apply it to a higher resolution observation, like the one I showed you in the first part. And because at the end, one is included all the variety that we will find in the high resolution observation. Or one can train a neural network of from an inversion of a set of pixels in the field of view to get a good guess model for the whole field of view, and then we can just use it for the guess model for the inversion code. So we will be very close to the solution, and we will only need a few iterations to reach the minimum. So this is very important because in principle with this very expensive method in terms of computations, one can only do an inversion of a small field of view. So at the end you will analyze only a single example or sample, but with this quick shortcut, one can get a guess model for the whole field of view and then do the inversion of the whole field of view in just in a few iterations and do statistics later of the whole field of view and well, in this case about the thermodynamical properties of the fibrils. So we wanted to go one step further. I have been showing since the beginning these convolutional neural networks and how we can use it to extract information looking to the surrounding pixels. And in this case, we train a neural network to infer the atmospheric properties decontaminated from the PSF. So what you see in those panels is first is the longitudinal magnetic field and the temperature. They has been showing at two different heights, and each row is the inversion results from a standard inversion code like here. The second row is the inversion result of the deconvolution of the data, and the last row is the output of our neural network after applying the neural network to the Stokes profiles. So another thing we did here was to show that only one neural network is also able to infer many quantities as we want from a single neural network. So in this case, we were inferring the temperature, the velocity, the three components of the magnetic field. And as we were doing the training based on a MHD simulation, we were extracting the physical properties in a three-dimensional way. It means that we were able also to provide information of the Wilson depression or the pressure, quantities that in principle are very difficult to obtain with the standard inversion techniques. And well, and as has been showing before, these techniques is around 1 million times faster. One of the problems that we found in this particular case was that we were not able always to fit all the profiles. And this is important because we were, our neural network was trying to learn the mapping between Stokes profiles and atmospheric parameters. And we were not fitting profiles. We were fitting, in this sense, the atmospheric parameters compared to the atmospheric parameters that were in the simulation. So we were comparing only the atmosphere from the simulation and from the neural network. But we were not closing the loop. What we have tried recently is if we close this cycle with a radiative transfer code, and we evaluate how these pixels has been fitted, we can improve the performance of the neural network by doing this cyclic approach. And in this sense, Chris Osborne has been trying a similar case with, and collaborators has been trying to do something similar with a different type of neural network, an invertible neural network, with a very smart approach where you see more or less the same picture here. They were trying to go from Stokes to atmospheric parameters and then again to Stokes, closing the cycle. But they were also using what is called latent space, where they were saving information about degeneracies and ambiguities. So you probably remember this plot because he was giving a talk here in this colloquium some months ago, and he was showing that he was not able to infer the quantities, but also to give the uncertainty of this quantity. Very important when we do the inference from the observed quantities. So this is very important, the information of the degeneracies and ambiguities, because we were used to work with a well-known Zeeman ambiguity at 180 degrees, but under the Handler regime, and in particular for the helium line at the 1030 angstrom, we can find up to 4 different configurations of the magnetic field that are compatible with the signals, and this can be found very easily with those neural networks that are able to map the whole space of parameters, finding where we have these ambiguities and degeneracies. So this is a work that has been where I have been working during last months. And finally, I also wanted to show you something different, not related with regression problems, about the classification and tracking. And well, we know that from the emergence of the magnetic flux, we will have reconnection events, and we will see these multiple phenomena in very different ways and in our observables, for example, in H alpha or in silicon 4 from IRIS. So this phenomena has been studied for many years, and we can classify them knowing the special features that they will produce in a certain spectral line. For example, element bombs, UV bursts, microflares. So it would be great to transfer this knowledge to, for example, SDO, where we have a great cadence and we have the full solar disk. So we would be able to do statistics. So one can train a neural network to learn this mapping and to transfer the knowledge that we have in certain wavelengths to create a mask where we say, okay, this is a pixel that belongs to an element bomb. This pixel is just quiet sun. This pixel is a UV burst. And then we can learn this mapping. These images are examples of a working process, but with a very successful results, where after training the neural network, we have taken the SDO data, we have applied the neural network, and we have recovered a detection map, like the one I showed you here, where we have some hints about where we have the UV burst or the locations of the microflare. So, well, I know I have been showing many different examples. So I just wanted to summarize in this last slide, saying deep learning can help a lot to handle the amount of data that we are producing and we will produce. I also wanted to share with you that these techniques are very useful for different things like image reconstruction, compression, denoising, parameter inference, classification and tracking. They can accelerate many computational expensive inverse problems like the one I have been showing here, where the solution can be checked in many cases by doing the forward calculation when it's possible. So from the inversion of the neural network, we can synthesize and check the profiles. The same with the deconvolution. We can do the deconvolution and check the results. But we have to know the limitations. And one of the most important limitations is the extrapolations outside the parameter space. We cannot use the neural network with data that has not seen during the training process, because of course it will not work. It has been not designed for it. And in my opinion, many of those examples are just the first step. We need to learn how to include more physics, or at least physical constraint in those techniques, so we can also not only improve the performance of these techniques, but also to get some physical information and physical insights from them, while also estimating uncertainties. That is very, very important, where we are just inferring quantities from observations. So this is all what I wanted to say. So thank you so much for attending the talk.
Thank you very much. If anyone has questions, if you turn your camera on, it can be easy for me to see anyone, or else feel free to type something in the chat.
I have one question. And I don't know anything about neural networks and how this works, so bear with me. But you talked about the cyclic approach, introducing the forward modeling to compare the results from the neural network inversion to the spectra, and that is actually part of the process. Is that not equivalent, or is it somewhat equivalent to just adding more traces to the training of the neural network? Because essentially you're calculating more pairs of spectra versus atmospheres.
Let me go to the same slide. This one, for example, right?
Yeah.
So in principle, this path could be our relative transfer code itself.
Yeah.
So here the neural network will be exactly the same. We are just adding a physical constraint, and
Oh, I see.
so the main difference is that when we are trying to match only the atmospheric parameters, maybe if we are not very accurate, for example, let's say we are trying to reproduce the whole stratification of temperature, but our neural network is not working well at one specific height, or then probably when you look to the profiles, probably this point at this height is very important, because the profile is almost is completely different, because probably the formation of the core is around this pixel. So even having maybe a small error in the temperature, this not implies that we will have a small error in the Stokes profile. So this is always important to close the cycle.
So maybe do I understand that you're using this as a form of regularization or something like that? So penalizing the neural network when the Stokes profiles don't match?
Yeah, you can see that like this. Yeah.
Okay, thanks.
Did you have a question, Ricky?
Yeah, I do. Hi, Carlos. That's a great talk. Thanks.
Thank you.
So the question I have is related to the denoising work. And you had noticed, how the neural network would return a smooth profile. And I'm wondering if when it's working with these noisy data, is it doing more than just returning a mean small profile from all of the data that it's learned? Or does it give additional information? Because you could imagine, the easiest way, if you have too much noise, if it's 100% noise, then there's really no information, right? But yet, if you assume that there should be a profile in there somehow, you just replace it with the mean, right? Is the neural network doing more than that, or not?
Well, in principle, it's difficult to say, because I will say that, for example, if we have a large patch of your region with similar profiles, you will probably end up with a median profile of the region. But what I have been also looking is that at the difference. So what I wanted to check is in the difference between the noisy image and the output of the neural network, because the first thing that I wanted to do is to not remove more information that the one that I have. So at least what I see in the difference, I was not getting some correlations on some patches, or something that could be a signal. Was only a random distribution of noise. So if look into that, you could think that as every pixel that you are cleaning in this way, they has been recovered by the neural network. But I think there is also a spatial scale, probably very close to the spatial scale of the noise, where you cannot only clean the noise, but you are probably cleaning the signal, because at the end, the neural network is like learning the distribution of the noise. So it will not work very well at those scales. But for things that are a bit larger, it will work much better.
All right, thank you.
Hi, Carlos. Okay. Yeah.
Sorry.
Yeah, please go ahead. Please go ahead. Yeah.
Thanks. Hi, Carlos. This is Sergio González Manrique from ISC.
Hello,
You are talking
Sergio.
about, yeah. You are talking about the denoising. I will continue with this this question about the denoising of the spectra. You are using this only for the iron line, or you are also could apply it for other spectral lines? You know that I'm using normally Gregor data, like you were doing your PhD, the 1080 line that you said. After that, it is possible also to denoise the spectra with that. Normally, I'm using PCA for that, but yeah, maybe it could be a better option to use your methods.
Well, I want to clarify two different things. The distribution of the noise probably is something that belong to the instrumentation and the telescope. So if you train a neural network with data with a telescope in different spectral lines, it could be applied, to whatever spectral line that you observe with the same telescope. Here I was showing the iron line, but all these examples were done with the calcium 8542. And I have tried the same neural network with other spectral lines, like the iron lines again, but not trained with the iron line. And as the instrument in principle is the same, is a CRISP at the Swiss Solar Telescope, and the statistics of the noise is similar, one can use it without any problem. But what you are suggesting is also a little bit different, because what I wanted to exploit here was the problem that we have in the Fabry-Perot, that is that we have only a few points. However, in Gregor, with a slit spectrograph, you have many points in wavelength. Yes. So my impression, I have been doing some tests, but my general impression is that using principal component analysis will be more than enough for extracting the information. It will be good to compare if one can get a similar thing. But another question related with a slit spectrograph is how can you train a slit spectrograph? Because what I was showing here with was crisp scanning. So we have like a full field of view taken at a certain time, right? And then a few seconds or some time, we have a full view that is again taken at the same time. But with Gregor, you will have a slit that is moving, and probably when you finish the scan and you start the scan again, things that were at the beginning of the scan at one, let's say, time frame, and the one that are in the beginning of the next scan probably have a difference that is quite large to have this assumption of different, where the main difference is the noise. So
okay, yeah, well, Maybe with the IFFU it could be different, because then the time that you are getting, you are taking the information, it will be lower than that. Of course, you have the slit and you need to have, I don't know, 13 seconds. You will need around 10 minutes to observe that. But if you use the IFU, so then it could be much faster than that. So then it will be a matter of seconds or a minute at most.
Could be a very interesting option to try and to study.
Okay, so maybe we can talk in the future then.
Thank you, Sergio.
Yeah, thanks.
Hey, hi Carlos.
Sovic.
This is Sovic from University of Oslo. Yeah, so it's a very nice talk, and you talked about so many things. I have many questions, but I'll come to two main questions that I felt would be worth discussing here. But maybe we can discuss others later. So I will start with this denoising thing. So you started with the assumption that that the images, like noisy neural network, you started with the assumption that the images which are closer in time, they are only separated by basically noise, right? You assume that the features in those two images that are closer in time, they do not evolve. So I was wondering, like you show this example in calcium 8542, and even in, for example, in a very, very quiet sun patch, taking the full spectropolarimetric scan in CRISP, it also takes like at least 15 to 20 seconds, I would say, like considering Stokes IQUV, or maybe more. And then I would actually consider, I would actually question that how good is that assumption valid, considering the fact that in chromosphere things really change rapidly and at the resolution of CRISP. So how will the neural network be able to kind of distinguish between the noisy features, or actually there are some features maybe which has evolved in time?
This is a very, very good question. I have been trying to realize how one can at least to improve the neural network, in the sense that the assumption is not as strong. And probably one could study and calculate the optical flow between these two images and see how they were evolving from one image to image. So this information can be introduced in the neural network, or can be, so you can take the second image and like go back in time or something like this.
Yes, but also you mentioned optical flow. It's a very interesting solution, but if I remember correctly, like optical flow, like if we just consider the problem with local correlation tracking, that's what you mean, right? You mean like images in consecutive time frames, you just do the local correlation tracking and you try to track the evolution of features in space
Yes.
with time. But if I remember correctly from Andreas's DeepWell paper, he clearly showed that the reason why DeepWell was developed and it's so powerful is because the local correlation tracking, they do not work well for features which are having a very high resolution below 1 arc seconds. And in CRISP, we know the resolution is far, far below, like it's close to 0.1 arc seconds, in fact. And in that case, I was actually wondering whether this problem will be solved by this local correlation tracking, because maybe the features will not evolve so rapidly for the local correlation tracking to actually detect them. And secondly, even if you consider, for example, if you consider Andreas's code also, like DeepWell, for example, he also showed that the accuracy of this proper motions, it actually kind of decreases if you sample higher atmosphere, right? It's way more accurate when you are sampling at log tau equals 0. But when you are sampling at the height of, say, 8542, which is roughly log tau minus 4 minus 5, between that, then the accuracy of DeepWell also falls. So in that case, how would you tackle it? Maybe, I mean, this is a too technical question.
No. Yeah, thank you. For the first part, well, I was talking about the optical flow, but true. If we found that if we find that there's something close to deep bell, so a neural network trained to mimic these optical flow motions could work better, we can use this software for this neural network and not just the local correlation tracking.
Right.
And also related with the second part, you were saying, yeah, that when we are trying to infer the transversal velocities in higher layers, where we have our it's lower because we don't have so much information about these layers. But it's also true that, for example, here what I'm showing are just images. So here I'm not considering layers in the atmosphere or things that are really moving related to velocities. Here I'm just talking about optical flow and how something bright is moving to the next pixel bright. So heights is not something fundamental at this point. So could be that something like what you are suggesting, like a deep bell applied to this case could help the denoising method to work better and to distinguish these small features and small motions and what is the noise and what not. So thank you.
Thanks for the explanation. And the second point, the second question was about this Ellerman bomb and the detection of these features. If you can go to that slide, I think, because Paul, I hope it's okay if I ask another question, right?
Yes, go ahead.
Okay, yeah, thank you. So the next one where you have this detection mask. Yes. So I was wondering, this is a really good approach to do it in terms of a deep neural network, to kind of have this detection mask and kind of have the signatures in different layers in the solar atmosphere by aligning different instruments. But I was wondering that could you just simply use like a classical machine learning technique like k-means, for example, because you are detecting these Ellerman bombs and these features from CRISP, I assume. And then you are kind of having that mask and trying to superimpose them on the different telescopes, right? On the different instruments, if I understand that correctly.
Yes, exactly.
Yeah, so each of these features, for example, Ellerman bombs, we know that it has really strong enhancement in the wings and not much in the line core if you observe in the H alpha. So you could just probably apply k-means and classify those spectra, and that whatever spectra corresponds to that particular representative bin belongs to Ellerman bomb, and then you can create a 2D mask. And then basically, if you just have aligned data, you can just superimpose those 2D mask, and that's probably much less computationally intensive. Or am I missing completely something here?
So in principle, the way that you create the mask in your data is one step. So as you explained, that the Ellerman bombs has a very important signatures in the wing of H alpha. So you can create like what is the typical profile that will look like an Ellerman bomb profile, and then you can use it for detecting Ellerman bombs in H alpha. But what I'm showing you here is how to transfer this knowledge about how you see the Ellerman bomb in H alpha to how you see an Ellerman bomb in SDO. So at the end, only using SDO, you can study if what you have in your pixel is an Ellerman bomb or not, without having H alpha or another spectral line.
Okay. So that's one step ahead. Okay, all right. Okay.
And of course, you were also saying that why a neural network and why not? Well, this is a very general question that also is related with all the methods. So here I'm not even saying that a neural network will solve it. This is a working process where we are also comparing with other techniques and trying to find why this is the best one or not. And so, yes, of course, one should try to think about how we are analyzing things and not just to apply what we have.
But I think you already explained this because k-means or this technique that I suggested will not work, because you are now actually after you train this neural network, you should be able to identify element bomb signatures irrespective of CRISP. You should see AIA 1600 and see, so, and that is not possible with an unsupervised machine learning technique because we don't have the labels, right?
Exactly.
So okay, thank you.
Thank you again.
So we're kind of getting a little bit over time, but there is a question in the chat. Arvind, do you want to ask that, or I can read it out if you prefer?
Yeah, I can unmute myself and ask. Carlos, that was a nice talk. If you can go to the slide where you have the invertible neural network.
Yes, this slide.
Right, this one. So that latent space, if I understand that correctly, I think I put that in the chat as well. So if you have, say, multiple solutions that correspond to one Stokes profile in the atmospheric parameters, and then that's what you call as degenerate, right? So how do you handle how do you end up handling the degeneracy? Because for an invertible neural network, I assume that the mapping has to be bijective, right? So it has to be a one-to-one, otherwise you can't go forward and backward. So how do they actually handle that? Do they just temporarily store the alternate degenerate solutions in the latent space and then you cycle through them during different training, or is it some other technique?
Well, the first thing is that probably this question can be answered much better by the authors. Sure. But I have been playing with something similar in the case that in this latent space you can save this information where from the same atmospheric parameter you will from different atmospheric parameters you will synthesize stock profiles that are very similar, and this is something that we cannot do with all the neural networks that I have been showing here, because they are fully deterministic and you cannot solve this problem. So using this latent space, you are exactly saving this information. So then when you are let's say sampling, because this is what he's really doing here, is like doing like a Monte Carlo, right? So he's sampling this latent space, searching for all the possibilities. So these possibilities can be just an unimodal distribution, or and the one I showed you here, you can have up to 4 or more, right? So this is one of the methods that are based on a Bayesian framework that try to deal with the whole parameter space and how to capture the information of the degeneracies and the ambiguities.
Okay, thank you. So there is a Bayesian element involved. Okay, thank you.
Yeah.
Okay, thank you again, Carlos. Nice talk.